Greetings from New Jersey Institute of Technology. I'm Mike Smullen, Director of Alumni Relations in the Office of Alumni at NJIT. I'm pleased to welcome you to our latest Highlander Chat, Solving Global Challenges with High-Performance Data Analytics. As a quick reminder to all of our viewers today, this is a live virtual streaming event, so we may experience some technical issues. Please bear with us as we move on from any of those. Without further delay, it's my pleasure to introduce our guest speaker today, Dr. David Bader. Dr. Bader is a distinguished professor in the Department of Computer Science in the Yingwu College of Computing and director of the Institute for Data Science at NJIT. Prior to this, he served as the founding professor and chair of the School of Computational Science and Engineering in the College of Computing at Georgia Institute of Technology. He's a fellow of IEEE, AAAS, and SIAM. It's my pleasure to welcome Dr. Bader today.
Thank you, Mike, for that great introduction. And I'm really looking forward to engaging with all of our alumni here at NJIT and on this channel. So let me share my screen with you, and hopefully you can see it pop up now.
And we are live with your screen.
Great. So I look forward to speaking about solving global grand challenges with high-performance data analytics. And I encourage any alumni who wish to reach out or engage more, you can look me up on our website. I have the URL there. I'd be glad to talk more in depth about some of the topics today. As Mike mentioned, I'm a distinguished professor recruited to NJIT in 2019 to found and direct a new Institute for Data Science that I'm excited to tell you more about today. And I've really served in some of the highest levels of government and collaborated with industry to give you my perspective on data science and what we're doing to really solve problems that impact people across governments, across populations, and around the world. So let's get into it. And here at NJIT, let me skip forward to the slide. I have launched an Institute for Data Science. So an institute collects up centers of activity, centers of excellence into a unified group. We had several centers existing at NJIT. One is a Center for Big Data that focuses on big data analytics, systems and tools, as well as cyber infrastructure that's led by Chase Wu. We had another cybersecurity research center led by Kurt Roloff and Reza Kurtmolla on practical encryption and homomorphic encryption technologies and information assurance on IT devices. And a third center that focused on medical informatics, supported by NIH and the National Cancer Institute. This center is led by Joshua Pearl and Jim Geller and is called the Structural Analysis of Biomedical Ontology Center. So these three centers were existing at NJIT. We moved them underneath this new Institute for Data Science. And recently with Stephen Taylor in the School of Management, we've launched a fintech group that's focused on the data science that we see in financial services and the insurance industry. These are two key areas in New Jersey and in the region for looking at large-scale data science. And finally, we are planning to launch this semester with Grace Wang, a Center of Machine Learning and AI that's focused on real-world technologies and industrial partnerships that are really ubiquitous now when we look at solving problems across academia, industry, and government. The Institute for Data Science also has a weekly seminar series. You're all welcome to attend Wednesdays at 4 p.m. You'll also find the lecture series off of our Institute's web page, datascience.njit.edu under events, or we have a YouTube channel for NJIT Institute for Data Science that collects up some of the previous lectures. There's some great speakers in this. The Institute itself has about 35 faculty across the current centers, and I think we're really doing some great research led at NJIT for problems that really matter in today's world. I am running the Institute for Data Science out of our brand new Jersey City satellite location. I encourage you all to visit. It is next to the Exchange Place Pass Station and just a short stop from Lower Manhattan. We're offering there a master's degree in data science for both returning students and part-time students who wish to take new degree programs and also certificates in the evening hours so that they can work full-time and be able to take some new courses in data science. This has been a great experiment. It's been running since the fall of 2019, and we've seen some great students come through this program already. So here's just another picture of Jersey City. We have Newark all the way in the background of this photograph, and the PATH train runs to Exchange Place on the lower right of this picture. And we're in line with a number of fintech companies like Goldman Sachs. JP Morgan Chase is just off to the right of the screen. But in the very center, you'll see NJIT sitting on the 36th floor of 101 Hudson, which is the Bank of America building here in Jersey City. So I encourage you all to visit, check it out. And we solve in the Institute for Data Science real-world grand challenges, and they come in many shapes and sizes. We look at problems related to urban sustainability, healthcare analytics, trustworthy, free and fair elections, insider threat detection within large organizations, utility infrastructure protection, giving attribution to cyber attacks and defending against them, all the way through disease outbreak and epidemic modeling. The hallmark of our work is really taking data and understanding how to let that data drive your decision making within organizations, and also to really improve the conditions that we have in this world. Now, in the last week, we received a new National Science Foundation award for a project that I'm excited to tell you about today. This is breaking news, hot off the press, where we received an award for $187,000 this year for doing high-performance algorithms for interactive data science at scale. There's been a big problem when we look at data science, where data is growing exponentially every year, and it's just overwhelming amounts of data. And previously, we could load a data set onto our laptop. We could use tools, for instance, in Python, some easy-to-use tools like NumPy and Pandas, and be able to explore those data sets. But as the data sets grow larger and larger into tens of terabytes, we no longer have space on our laptop or the time needed to solve these massive data analytic problems. So we are innovating in new technologies, new capabilities to have a Python library, so easy to use productively from Python, where you can call the work that we are creating inside a toolkit called Arcuda. And on the back end, you can have a supercomputer that is analyzing those data sets and doing it interactively and in real time. So you have the ease of manipulating massive data sets, but the productivity and the interface that you're used to with Python front end. And this is just hot off the press. This morning, NJIT released this news story about the award. Institute for Data Science aims to democratize supercomputing with NSF grant. So we're trying to let everybody be able to be in the world of massive data analytics without the need for special infrastructure and special knowledge of how to explore those data sets, but to be able to do it interactively wherever you sit. Now, data science has really been something that has been blossoming the last few years. I was very proud to be a part of the Obama administration's National Strategic Computing Initiative that was launched in July 2015 by executive order to really advance the US leadership in high performance computing. it laid out a 5-year roadmap for the country of how to invest in strategic computing so we would be able to really solve the computational and data science problems that are most impactful to our industries and the country itself. We've also seen reports from the National Science Foundation, from the National Institutes of Health, and other analyst firms that have talked about the need for data-driven technologies, for instance, impacting $300 billion worth of value to the US healthcare sector alone by having data-savvy managers. So there's a real thrust these days for training and hiring, bringing onto our research teams data scientists who know how to both engineer data science systems, but also do the analytics that are necessary. And I should say some of the certificates that we're running through NJIT at Jersey City really train students in the technologies and techniques that are needed to form that new workforce and a diverse workforce for these data savvy managers. Now, in 2019, the previous White House administration updated the National Strategic Computing Initiative. And again, I was glad to be a part of this federal effort. And a report came out in November 2019 that updated the previous plan and really spoke to a 10-year roadmap for the country of what needs to happen in terms of innovative computer hardware that better addresses data science challenges, for new software infrastructure to be able to develop our applications, and really the partnerships needed between academia, industry, and government to solve the problems that are really the ones that are most pressing, the global grand challenges that we need to address. So in the center of the screen, you'll see my 5 minutes of fame on Twitter as the US Chief Technology Officer at the time, Michael Kratsios, retweeted my tweet about the new updated report. We also work very closely with industry. So here we have an award from NVIDIA on an AI lab, or NVAL, where we're building out open source data science accelerated toolkits in the Rapids AI framework that NVIDIA has made available to the community. So a lot of the technologies that I talk about today in terms of data science and graph analytics are included within NVIDIA's projects. We also work closely with other companies like Facebook. In 2019, I received an AI Systems Award from Facebook for looking at scaling up graph learning algorithms, which is a type of representation learning, but to do it at the enterprise scale. Now, when I talk about data science, I often like to use these quadrants where on the x-axis, I have objects from known objects on the left to unknown objects on the right. And I have patterns from known patterns on the bottom to unknown patterns on the top. So in data science, often we're either looking for patterns within data sets, or we're looking for particular items, which I call objects here. In the lower left-hand quadrant is the type of technologies where we have known objects and known patterns. In the 1980s, the database community gave us relational databases that really helped us solve the problems in this quadrant, where we have particular schema, and that includes tables with keys that point into other tables. For instance, we may have a table of customers, a table of parts, a table of purchases that are made, and we know how to operate very well in this space when a query comes in that says, tell us all of the items a particular customer ordered, or tell me about the customers who typically order or purchase this type of part. We're very good at solving those types of problems with relational databases. In the 1990s, we got vertical databases, and they helped us solve problems in this upper left-hand quadrant where we have known objects but unknown patterns. So an example here may be from cybersecurity, where you're the chief information security officer of a company, and you're able to monitor the actions of your employees, but one of your employees keeps triggering an alert. Maybe they're accessing files that they shouldn't be accessing. Maybe they're printing out material that shouldn't be printed. Maybe they're just peeking into finances or other places where they don't have that access. And so what you want to do is figure out, is this person just making some accidents, or are they up to some nefarious means, and are they in collusion with other employees in my company? So here you have known objects, which are the alerts, but then you're trying to figure out the patterns of what they're doing and classify it as either something that is malicious or something that is just a mistake that they made. In the lower right-hand quadrant, we have a similar type of problem represented here as a graph where we have a pattern that's known, and then we may have some unknown activity, some observed activity. And what we're trying to do is match that pattern to the observed activity to see if it occurs. So in this sense, we often do cybersecurity in this way, where we have patterns of network traffic that may represent a denial of service attack or some other type of sophisticated attack, such as APT, Advanced Persistent Threat. And we look through known traffic to see if that occurs. And if it does, then we know that we've found a specific type of attack within our network security. But what excites me is this fourth quadrant on the upper right that I call unknown unknowns. And in this fourth quadrant is data that we really want to explore, where we don't know what the patterns are and we don't know what the objects are. This is where all of our surprise sits. And what we want to do is make sense of this data. And this could be, for instance, a new type of cyber attack that we want to defend against, but we haven't seen yet. Or this could be a new medical case that we have not witnessed, or the blossoming of a new pandemic globally that is occurring, but we may not know about it until it's already spread. So this is a very important area in data science to explore, and we need a lot of tools to be built, a lot of algorithms and tools to be able to answer questions that come in this space. So I'd like to talk about these in terms of graph and graph data science. A graph, very simply, is a representation of data where the objects are vertices in the graph, and the edges represent connections between those objects. So when I see two computers talking with each other, I may add an edge between them that tells me at what time those two computers exchanged a message and what type of message was it, how long was the message, and take all of these actions together and start building up this graph. For real-world graph challenge problems, these graphs aren't static, but they're constantly evolving. They're constantly ingesting new data, and I need to be able to keep up with that fire hose of data and build these graphs at the very same time. So I call this exascale streaming graphs. And this is the area that I've really pioneered. And we've worked on problems from healthcare, where we may be looking at the pandemic spread of disease. And in the past, we've looked at SARS and avian flu and H1N1 swine flu. Here, this has been quite useful because we could dust off the work that we've done and apply it to the COVID-19 pandemic. We've also looked at massive social networks and understanding communities, how they form, what are their intentions, population dynamics, how pandemics spread within communities, and also transportation and evacuation, especially during a natural disaster. What do people do to remain safe? We've looked at business intelligence and anomaly detection. We've looked at problems in systems biology, for instance, understanding the mysteries of the HIV virus, and also understanding life itself, understanding disease, working on problems of drug design, looking at microbes within the soil, and so on. The electric power grid, I'll give you an example of that coming up, is important for everything from communications to our transportation systems, generating energy and supplying it to the population, even our water and food supply. So we've looked at problems of resiliency in the electric power grid, all the way through to modeling and simulation of full-scale economic, social, political simulations of entire nations. So this is an area that is evolving, and we now have data sets and infrastructure, cyber infrastructure, that lets us solve these types of problems in real time and at full scale. So let me take a step to the side and tell you more about graphs. And they're really pervasive in large-scale data analysis. I mentioned before that graphs have vertices and edges, but there are many, many types of graphs out there. They're used in computational science and engineering simulations, in experimental devices, in modeling the internet and its traffic, and different types of scientific applications. But it's very challenging because the data sets that we see may have different data sizes. There may be heterogeneity to the data that we collect. In fact, we may have new types of data that we collect in the future. Also, these observations may have different types of uncertainty related to them. There may be noise. There may be different bias of collection in the data sets, and also varying data qualities. So here's an example of 3 applications, one in astrophysics, one in bioinformatics, and the third in social informatics. If I look at the leftmost figure in astrophysics, we may be looking at digital sky surveys, for instance, the Sloan Digital Sky Survey, which has massive, massive data sets looking up at the sky every day. And we may be interested in finding pulsars and turning a radio telescope towards them in the few minutes from observing it in the focal plane to being able to observe it in with a scientific instrument. So what we want to do is outlier detection. Take 2 images of the same portion of the sky, compare them together, and look if there are temporal variations. So a challenge of doing this, as I mentioned, is these are massive data sets. Some of the biggest data sets in science come from these sky surveys. And the graph problem that we want to solve is clustering or matching of these different celestial bodies together to figure out what are the outliers and our potential pulsars. In the middle image from bioinformatics, we may be interested in identifying drug target proteins that are very useful in drug design. And the challenges that we have is this data is typically very heterogeneous, coming from different laboratories and different sampling techniques. So we have a wide range of qualities of the data, and the graph problem that we may want to solve looks like centrality or clustering of these proteins together. The third example comes from social informatics, where maybe we're trying to discover the emergent communities within a social network or understand how information and disinformation spreads within social network applications. So the challenges are really that we may need new analytic routines and have a lot of uncertainty in data. Maybe we have missing data or erroneous data that we have to overcome. And the graph problems may look like clustering or shortest paths of information between vertices, or even flows of data between the people within these social networks. So again, we have many types of graphs. There is not just a single canonical graph when we look at data science. And when we're developing techniques, we really have to tailor it towards the type of data that we have, and then what type of problem we're trying to solve to be able to pick out what are the right algorithms. So I mentioned previously we've worked on the resiliency of the US power grid, or the power network. Here's just a picture and a headline from the New York Times talking about blackouts that we've had that occur due to failures in the grid. The grid could be modeled as a graph where we have vertices representing transmission points, and then lines are really the conduits that serve power. And again, we primarily have an east and west power grid within the US. We've seen Texas, recently is on their own grid. And these grids typically have a lot of work that needs to be done to mitigate these risks and really to make them more resilient to particular types of failures. In network analysis for intelligence and surveillance, here I have two graphs pictured. On the top is a public image that represents the hijackers on September 11th in this terrorist network. And it was argued that if we could have done graph analysis and an analytic called centrality or betweenist centrality, we would have been able to pick out the hijackers and even the ringleader of the hijacking through this public data. On the bottom is another image from communications of the ACM that represents this subgraph isomorphism problem or pattern matching that I mentioned previously, where we may have a pattern. Here, there's two people, they live together in a house, one rents a truck, the other is buying fertilizer, and they're observing a factory. Well, that may be a risk. So what we want to do is find in observed activity something that looks similar, maybe not exactly the same pattern, maybe there could be edges removed, but we're trying to find this pattern within the observed data and maybe hand that off to a security official to take a closer look. Also in public health, I'll tell you about just a little snippet of a problem that we're very proud of for working on, and it was looking at the human proteome and trying to understand the disease implications within the human proteome. So we took, at the time, 44,000 protein interactions within the human proteome. So all of the protein to protein interactions that were known at the time we did this study. And we ran an analytic called betweenist centrality that is looking at the importance of these proteins within the proteome. In fact, in this work, we were the first group to parallelize or accelerate the performance of doing this very expensive calculation. What I have pictured here is just a snippet of the results, where on the x-axis, we have the degree of each protein on a log scale, namely the number of proteins that each one interacts with. So on the left are proteins, each dot represents a protein. On the left, they interact with very few other proteins. On the right, they interact with anywhere up to 100 proteins. And on the x-axis is the log scale of the betweenist centrality. So vertices at the top represent proteins that are going to be higher in importance. And what you see is one protein with the highest betweenist centrality that is like finding a needle in a haystack, which is a protein that was implicated in breast cancer. So these types of techniques are very useful for solving the problems that we've heard about many times for finding a needle in a massive haystack. And the important part is it's not always the data that interacts the most, it's often the ones that are more critical to the structure of the network that are going to be interesting in these types of studies. So as we go through graph data science, there's a lot of decisions to be made. And this is what our students are trained in. For instance, trying to figure out the right type of problem to solve in this graph abstraction that matches the real world problem you're trying to get the answer to. So there's many different graph algorithms. The different factors within the graph may influence the algorithm that we choose. For instance, is the graph very dense with edges, or is it sparse? Are there weights on the vertices or edges? How big is the problem? And so on. And then we could try to solve this problem in a number of different ways. One would be to look at it as the ad hoc graph that we construct, or we may be able to look at it with a different view, for instance, with sparse linear algebra or linear programming types of computations. So there's many different frameworks and views for solving these types of problems. Now, I talk about this in terms of moving from traditional high-performance computing to what we see today, a need for streaming analytics. So traditional high-performance computing is where we use many computers together to work on one data set. This is great when we have static data sets and in forensic analysis, where we can load all of those data sets into a computer and really look at crunching those data, that information, to understand what's happened in the past. Streaming analytics is really a new way of understanding data science, where what we want to do is predictive analytics. We want to ingest very quickly the changing data that we see and be able to get out in front of the problem. So we want to predict that there will be a catastrophe before it happens so that we can prevent it. So this is very different from just reporting the news that's happened to being able to really predict the future. And our team at NJIT is working very hard on algorithms and new systems for doing streaming analytics. So maybe for the sake of time, I'll skip through some of these slides and come to this one where I explain how we turn a real world problem into these graphs and what the overall framework looks like. So often we have a user, and I'll just give the example coming from social network analysis, but really any application that we try to improve is going to convert from the domain of the application into an abstract graph. So here we have a tuple that says person A at time 1 is going to have an action like poke to person B. So here's person B, and maybe at time 2, person A will send a message to person C. And also concurrently at time 2, person B has received the poke from person A that was sent at the previous time period. And this continues, so every action that happens will basically generate a tuple. And we get all of these tuples in real time, and we feed them in as edges. So every one of these tuples looks like a directed edge between the two people. There's a timestamp and maybe some action that's taking place. And we feed that into a big computer that's able to store this graph or build this graph in memory as it witnesses these edges. So here's an example of what that graph looks like. And at the very same time that that graph is being built, we have analysts who want to ask questions from that real world problem, who are going to convert their questions into an abstract graph question, and they're going to query or interrogate this graph that's held in memory. So this is a bit of a cartoon of this slide, but often what happens is we don't have a single question, but we have multiple questions concurrently coming from these analysts asking questions of this data set. Now, because time is included in the data, these questions could be very simple extensions of traditional graph queries. For instance, did person A send a message to person B within this window of time? So we could add time to traditional types of static graph questions by looking at a window of time or at a particular instance in time, tell me how many people were in my graph. But what we also have the ability to do is have change detection. For instance, tell me anytime the shortest path between these two people has become dramatically shorter. So that's a change detection type problem. But we also get into fully dynamic analytics. For instance, we may have communities within our graph, and we may want to ask a question such as, did someone who was core in a first community at some point later in time become core in an opposing community? So can we find these movements or changes within the community structure? So it's a very interesting way to engage and look at these problems. Now, I think maybe in the last couple minutes, I'll tell you a quick story about looking at Twitter. This is actually work that we did about a decade ago. About a decade ago. We were the very first group to ingest a full take of public tweets. These were the same tweets going into the Library of Congress at the time, and analyze it in terms of graph analytics. We took a couple terabytes of data from September and October 2009, and we want to understand during a breaking event, how do people get their information? And we formed a graph out of those tweets. We looked at every Twitter follower and followee, and we constructed a graph. And then we looked at some breaking events. So I'll focus on the first one, H1N1. And at the time in 2009, H1N1, a variant of influenza, was predicted to have double-digit mortality, this pandemic spread of influenza. And we didn't really know how it was going to affect the populations, but there were some very dire consequences. Now, this work, as I mentioned, has been dusted off and used also for COVID tracking. But here's an example of what we did to provide these capabilities. We created a graph, and then we looked at computing between a centrality, namely the most important or influential handles where people were getting their information from on Twitter. We had some, the results are here, and it's ad hoc. We have the top 15 handles that we saw. Some of them are expected. For instance, the Centers for Disease Control and Prevention is ranked 1, 4 is flu.gov, 12 and 13 are CDC Twitter handles, and etc. So that was good that we're able to pick that out. But also we had commercial media, for instance, the New York Times at number 5, CNN at number 8, Time Magazine at number 11. That was great. But the surprise that we had was being able to find a Twitter handle like number 3 during a breaking event. I am here virtually coming to you. I don't have a live audience in the room here, so I can't see a show of hands of how many of you have heard of the official PAX handle. But I'd be willing to bet that none of you would think of tuning into this Twitter handle during a breaking health event. It turned out that official PAX is the Twitter handle of the Penny Arcade. It's a gamers group, and these are mostly adolescent males. And in fall of 2009, they were having a meeting in Seattle in the US. And they were the first group to all contract H1N1. And they started tweeting with each other, you know, what are the symptoms? How bad is it? Did you die yet? No, I'm not dead. Are you dead? No, I'm not dead yet. And this was a way where people got firsthand information on the symptoms of H1N1, how deadly it was, etc. And this is really the hallmark of these techniques. This was a surprise. And so in a breaking event, being able to tune in to these types of handles and understand the primary news sources, I think is very, very impactful. So let me wrap up here and take some questions. I'll skip through a lot of these slides that talk about the software that we've been building and some of the augmented use cases. But just to conclude, that data science is really coming of age. And being able to solve these massive scale analytics is going to require techniques like high performance computing, infrastructure and cyber infrastructure, new streaming algorithms, and something that I didn't mention during the talk with you today, but being able to do this in an energy efficient manner. Energy and our power is really a limiting factor in today's computing and a very important first principle for design of everything that we do. And mapping these applications to the right architectures may yield performance improvements that are 6 or more orders of magnitude higher in performance. This is especially important as we look towards more problems in machine learning and AI, where there's new chips and new designs that are tailor-made for data science. And again, I want to come back to the impact. What we want to do is solve real-world grand challenges, including urban sustainability, healthcare analytics, having trustworthy, free and fair elections, insider threat detection, utility infrastructure protection, cyber attack defense, and also being able to monitor disease outbreak and epidemic spread. These are just the types of problems that we can't afford not to solve. We really need these. Some of these are existential to our very existence. And so these are the problems that we really are focused on at our Institute for Data Science at NJIT. I just want to acknowledge a couple of the folks who worked on the material that I presented here. My research scientist, Dr. Jihua Du, a PhD student of mine who's fantastic, Oliver Alvarado Rodriguez, former PhD student, Oded Green, who's now at NVIDIA, and then some of my lab's alumni, Dr. Isha Nathan, who's at Lawrence Livermore National Lab, Vipin Sachdeva, Dr. Anita Zashrushka, who is at Trovaris, Dr. Louise Mungua, who's at Google, Professor Kamesh Maduri at Penn State, Dr. David Ediger at GTRI, Professor James Fairbanks at University of Florida, and Dr. Sunghua King, who's now at NVIDIA. So I want to thank everyone for spending your noon hour with me today here on the East Coast. And maybe I can stop at this point and see if there are any questions.
Well, David, I want to thank you so much for that wonderful presentation. I'm happy to say we have a number of questions, and I'm going to display some of those on the screen. So one of the questions we have is a little bit beyond my awareness. One of our questions that came in was, we use FPGAs with programming language VHDL and work in teaching. Are FPGAs useful for data analytics? And how does a partnership operate between NJIT and a manufacturer like Xilinx or for FPGAs?
So that's fantastic. And I should mention that a number of years ago, I was a Xilinx University professor working very closely with FPGAs. In fact, I've worked with FPGAs throughout my career, starting in the early 90s. And FPGAs are fantastic for doing early prototyping of systems and also for signal processing applications. We see a lot of use of FPGAs for data analytics. And once the algorithms are more firmed up, then we see those FPGAs being converted into custom ASICs to give much more performance. So whoever asked this question, I'd love to have a chat on the side with you. In fact, we have been funded to look at accelerators for data science problems using both FPGAs and other accelerators such as GPUs from NVIDIA. We've worked with companies like Intel and Qualcomm on graph acceleration chips, for instance, under the DARPA Hive program. And I have a lot of interest in collaborators who are doing FPGA design. So I think that FPGAs have been with us for some decades, and we'll continue to see them very useful whenever we can find a way to bring those data sets into the FPGA. They're very good at now the data bandwidth in and out of the device. And we see that we can have very special purpose designs mapped to FPGAs. So again, it's a great question. And it's really a timely question as well.
And I'll make sure to make connections with you, Dr. Bader, and those who ask the questions as well at the conclusion of the event. So we have a few more questions, and you'll see these sort of came chronologically through as you were doing the presentation. One of them goes back to one of your earlier slides. How do you verify the reliability and validity of, quote, unknown data?
So that's a fantastic question. Often we refer to it as V&V, and it is a challenge to verify and validate this data. So what we're doing now is providing tools to explore these large data sets. And let me just give you an example. Often in algorithms, we may run on a laptop on a graph, and the error rate is 1 in a million. So our answers that we get, it's usually pretty clear. We can look at them. We may have thousands or hundreds of thousands of items. If the error rate is 1 in a million, we almost never see an error. But as we move up to data sets with trillions of items in them for high performance data analytics, if the error rate of the algorithm is still 1 in a million, we're just inundated with errors. For instance, we worked on a DARPA program called Atoms for insider threats, where this was the case where we needed multiple signals, multiple indicators to be able to increase the fidelity of the algorithms and reduce that error rate significantly so that 1 in a million, which was no longer good enough, we needed 1 in a trillion to be able to operate successfully. So again, there are many different areas of using data. Looking for unknowns is reducing the risk of being surprised by data of something that's novel that we haven't seen before. For instance, the COVID-19 SARS pandemic was something that we knew such an event could occur, but we hadn't seen the genetics of this particular strain before. And the verification normally then goes to a human. So in many of these cases, we have a human in the loop where what we're doing is trying to take the human and not present them with 10,000 things to look at, but maybe give them the top 3 things to look at that are going to be the most important. And then we really need a human in the loop to do that ultimate review. So what we're really trying to do is reduce the load, use the computer what it's good at to reduce the load, and then again, doing the verification by the same manual means that would have been done previously.
So somewhat on that note, one of the questions that came in is, how do you normalize that data? Is there a standards body that does this, ISO or something like that?
So that's a great question, and it really depends on the application area that we're looking at. In some areas, such as network traffic, there are canonical representations for data sets that we can share around and we can look at. But if we're looking at, say, social media data, or we're looking at other areas, there may not be any standard. And in fact, using graphs, we can put together data of many different types. For instance, I could try to understand communications by putting together information from Facebook and Twitter and LinkedIn and Instagram. But who knows if a year from now there's a new social network that hasn't even been thought up yet? How do I integrate that with our current data analysis? Graphs provide a great way to ingest those new different data types that we haven't even thought of before. So I often think of using standards such as IEEE standards bodies. Once something has been calcified, it is really hardened and formed. But in these data science areas, we're really trying to pull together many different things that may not have been merged together before.
So there's a lot of themes to some of the questions that came in. One of the ones that came in from a couple different questions was, how do you ensure that biases are removed from the conclusions that you draw?
So that's a fantastic question. And I always argue when someone says that they have removed biases, there's no way to remove all biases. We have biases on the data that's available to us. We have biases that are generated by collecting the data. We have biases through the questions that we ask. There are biases in the algorithms that we run. And so it's never feasible to remove all biases. But what we would like to do is reveal what those biases are and understand how those biases impact the decisions that we make. So we would always like to reduce the biases, but to think that we could remove it, I think will be problematic. So I would find a way to discuss the uncertainty that we have within the data, and also the biases from collection and from our techniques. And I think that's the conversation that really needs to happen, because at the end of the day, we want systems that are going to make the right decisions, that are going to understand that we have diverse populations, that we can't always look at data to understand how humans behave and react. And if we just look at it in a very sterile environment of this is what we've seen before, well, in the future, that means we're only going to see the same things. But I'd like to think that the world is changing, and we really have to figure out a way to talk about data with those caveats, with those with a discussion that we can really let the general public know the power within those data sets, and to be very careful about revealing what those biases are.
So I think that's an interesting discussion to have. A lot of what you're describing here is a question of transparency, right? So those things exist, but people need to know that they exist. It needs to be demonstrated along with the conclusions that are drawn. One of the follow-on questions to that was, how do you maintain privacy? I noted that you did a big review on Twitter. By the way, I actually read some of those Penny Arcade cartoons at the time. I remember that when it happened. I didn't realize that was taking place, but it's so funny to see how interactive that was. But the thing is, when you're doing all of this analysis and you have to, demonstrate biases and so on and so forth, there is a question of privacy, I think, especially now. So does that factor in to what you do, or how you're drawing conclusions on things?
So privacy is an extremely important topic. And in my research, I'm typically looking at the algorithms and the techniques. And privacy is a layer that's going to occur prior to the work that we do in providing the tools to really analyze these massive data sets. So privacy is extremely important. In the work that I discussed, all of the data that I used was public data. So there's no expectation of privacy. For the insider threat work that we did, we're using systems at an organization, a large defense subcontractor, where every employee would be alerted and had to explicitly agree that all of their actions on their computer system were being monitored, and not only could be monitored, but were being monitored to look for insider threats. And so in the cases that we look at, we really try to make sure that privacy is respected and that all protections are maintained. Now, it's funny you mentioned that the Penny Arcade. That example also had an interesting data point. On one of the top Twitter handles were the Backstreet Boys. And I discussed this data at a number of meetings. Most of the time, I had nobody who knew what the Penny Arcade was. I'm glad to see that you saw the cartoons of the time. But I was in India giving this talk, and in the audience must have been the Backstreet Boys' #1 fan, who could not understand how the Backstreet Boys were included in this. And frankly, I didn't know either. So we went back to the data, and this was a great example of a false positive, because the Backstreet Boys were releasing an album at the same time. I guess maybe a CD for some generation, or maybe a new tune download for those today. And people were tweeting, "Hey, do you have H1N1? Oh, and did you hear the new Backstreet Boys?" So that's just a false positive where once you go back to the data, it stands out. But that question really got to me, and I think as we talk about privacy and protections, you can't just take the answer and use it. You have to understand. There has to be trustworthy machine learning, trustworthy AI, trustworthy data science, where you also have explainability and understanding of the answers. Because we'll be in a very dangerous world if we don't understand how we got those answers. And as was asked previously, was privacy protected? Were we taking care of all the biases to understand what we had? And so I agree that it's a great area to continue to research and look at. And I should mention, just a plug, on YouTube, you'll be able to see our data science seminar from last week with Dr. Cynthia Rudin from Duke University, who's got a fantastic talk about trustworthy AI. So I encourage you, if you're interested, to take a look on YouTube at our channel, NJIT Institute for Data Science, where we have some of the forefront thought leaders giving their views on some of the issues that we talked about today.
And I'll make a point of sharing that in our follow-up to this particular event. So you mentioned artificial intelligence. One of the questions that came in was, what impact, if any, is artificial intelligence having on your computations right now?
So that's a great question. And I talked a lot about graphs. Often graphs are used as input for AI problems. For instance, I mentioned the Facebook AI systems research where they're looking at graph representation learning. So how do you take a structure of a graph and get a vector that you could use in AI? Or within an AI problem, you have graphs such as deep learning is really a network. So somehow graphs and AI go hand in hand. But I think that the real aspect that we're seeing is that AI requires a lot of compute cycles for training AI models. And the types of architectures that are needed are being built with our understanding now of the algorithms for data science and also the needs for AI, not just today, but what we expect to see going out 5-10 years into the future. So I've been pleased to be able to work with companies such as NVIDIA, IBM, Intel, Qualcomm, and other chip designers to influence the architectures that we have today so that they're able to solve these types of problems. For instance, back about 20 years ago, I collaborated with IBM on a DARPA program called Ubiquitous High Performance Computing. Actually, no, it was DARPA High Productivity Computing Systems, HPCS. And we produced the chip and the infrastructure needed for IBM Watson that played Jeopardy. I also later worked with NVIDIA on the DARPA Ubiquitous High Performance Computing Systems program that gave us the general purpose GPU that's now a workhorse and used in all, or I should say in a majority of the top 500 supercomputers in the world to accelerate computation and data science. So the ability to influence the architecture is a much longer roadmap than the algorithms work or the software work. But we're doing that influence from NJIT, working to influence other chips and cyber infrastructure to be able to solve the problems that we'll need in industry and government in the future.
All right, that's great. So in the interest of time and being respectful of your time as well, we're going to cover two more questions. One is, how is NJIT planning to grow this program in order to compete against other educational institutions? And as a sort of a side question to that, do you use NJIT visual design students as part of your program?
So that's a great question. And I should mention that we've been running a master's degree in data science since 2017. In the fall, we have a planned launch of a new undergraduate degree program of a bachelor's of science in data science. I don't think of it as competing with other academic units. In fact, we collaborate very closely, and I think that collaboration is necessary to really provide the best education and train our students to work in the real world. We at NJIT are a partner. I'm on the leadership team of the NSF-supported Northeast Big Data Hub that collects up the institutions in the Northeast section of the United States for providing the education and tools needed for big data and data science. So we at NJIT are very well situated. In fact, New Jersey has one of the biggest needs in this region for those that are doing data science. We should also see in fall the creation of a new department of data science at NJIT. So these are really pioneering activities of NJIT where we're creating new academic discipline, we're creating new programs and new departments, and are really among the first in the nation to lead the way for solving these types of data science problems and training that workforce, a diverse workforce that are able to look at the problems within industry and government and really have impactful ways of improving the methods and solutions and interfacing across disciplines, interfacing from those in finance, those in health, those in security, those in arts and entertainment, and produce those well-rounded students who can really solve those real-world problems.
All right, and our final question from the audience: what are energy efficient strategies for practicing data analytics?
So for energy efficiency, that could be a whole other talk, and I didn't mention as much in this detail, but most of the energy is spent moving data sets from either place to place geographically or within a computing system. So the number one best way to improve energy efficiency is to try to collect the right data and use it in its location as much as possible before having to move that data set around. So the full answer would be another lecture or several lectures. But for energy efficiency, it really is collecting the right data, so minimizing the data set that's needed, and then minimizing the movements of that data set in order to produce the results that you want. So sometimes that also means rather than moving the data set, it's much easier to take your computation and move the computation to the data rather than moving the data to the computational engine.
Okay, David. Well, it sounds like we have another Highlander chat on the horizon then.
Sounds great. I look forward to it. Great question.
So, David, thanks again for joining us. This has been a real pleasure. As a reminder to the audience, please continue to submit your questions. I'll be happy to connect you with Dr. Bader at the conclusion of this event. And David, thanks again.
Thank you so much. And thank you for everyone for joining. And I look forward to meeting with and chatting with many of you in the future.
Thank you. Okay, as a reminder, this was our latest Highlander chat with Dr. David Bader, Distinguished Professor in the Department of Computer Science in the Ying-Wu College of Computing and Director of the Institute for Data Science at NJIT. He is a founding professor and chair of the School of Computational Science and Engineering at the College of Computing at Georgia Institute of Technology. He's a fellow of IEEE, AAAS, and SIAM, and an all-around stand-up guy. He's a fantastic faculty member, one of our stars, and truly devoted to his cause. So for all the alums who are watching, please make sure to stay in touch with us. You're going to read more news about what Dr. Bader is working on. As a matter of fact, if you listen to the beginning of the broadcast here, he teased some of the news that just came out of his department. So please stay in touch with us at njit.edu or follow us on social media. You can also follow this and other Highlander chats on our social media on Facebook, Instagram, LinkedIn, Twitter, and at our website, njit.edu. As I like to say at the conclusion of all of our broadcasts, go Highlanders.